guys! Welcome to our channel. This is Angel M. Pabalay, and for today's video, we're gonna vlog about deformation of rocks. And I want you guys to listen and watch on this video because I believe deformation of rocks is one of an essential topic in geology for civil engineers. And it would be helpful for us to become successful engineers in the near future. Fighting future engineers. Deformation of rocks. Did you know that within the earth, rocks are continually being subjected to forces that tend to bend them, twist them, or fracture them? When rocks bend, twist, or fracture, we say that they deform, change shape, or size. The forces that cause deformation of rock are referred to as stresses. So, to understand rock deformation, we must first explore these forces or stresses. Stress is a force applied over an area. One type of stress that we are all used to is a uniform stress called pressure. A uniform stress, sometimes referred to as confining stress, is a stress wherein the forces act equally from all directions. In the earth, the pressure due to the weight of overlying rocks is a uniform stress. However, if stress is not equal from all directions, then we say that the stress is a differential stress. Three kinds of differential stress occur. First, differential stress is tensional stress or extensional stress. This stress which stretches rock. So this is an example of tensional stress. Next is compressional stress. Compressional stress which squeezes rock. Next is shear stress. Shear stress which result in slippage and translation. So as we can see in the picture, shear stress is somewhat it has its slippage. When rocks deform, they are said to called as a strain. A strain is a change in size, shape, or volume of a material. Next is the stages of deformation. When a rock is subjected to increasing stress, it passes through three successive stages of deformation. First stage is what we call elastic deformation. Elastic deformation, wherein the strain is reversible. Next is ductile deformation. Ductile deformation, wherein the strain is irreversible. Next is fracture. Fracture is the irreversible strain wherein the materials break. How a material behaves? Well, it will depend on several factors, and these are: first is the temperature. Next is confining pressure. Next is strain rate and composition. Temperature. At high temperature, molecules and their bonds can stretch and move. Thus, material will behave in more ductile manner. At low temperature, materials are brittle. In confining pressure, at high confining pressure, materials are less likely to fracture because the pressure of the surroundings tends to hinder the formation of fractures. At low confining stress, material will be brittle and tend to fracture sooner. In strain rate, at high strain rates, material tends to fracture. At low strain rates, more time is available for individual atoms to move, and therefore ductile behavior is favored. And the last factor is composition. Composition. Some minerals like quartz, olivine, and feldspars are very brittle. Others, like clay minerals, micas, and calcite, are more ductile. This is due to the chemical band types that hold them together. Thus, the mineralogical composition of the rock will be a factor in determining the deformational behavior of the rock. Deformation in progress. Only in a few cases does deformation of rocks occur at a rate that is observable in human time scale. Abrupt deformation along faults, usually associated with earthquakes caused by fracture of rocks, occurs in a time scale of minutes or seconds. Gradual deformation along faults or in areas of uplift or subsidence can be measured over periods of months to years with sensitive measuring instruments. Next is evidence of former deformation. In such a thing, we will not believe if evidence does not exist, right? That is why we need evidence. Well, evidence of deformation has occurred in the past and is very evident in crystal rocks. For example, sedimentary strata and lava flows generally follow the law of original horizontality. Thus, when we see such strata inclined instead of horizontal, evidence of an episode of deformation. In order to uniquely define the orientation of a planar feature, we first need to define two terms, and these are the strike and dip. For an inclined plane, the strike is the compass direction of any horizontal line of the plane, and the dip is the angle between a horizontal plane and the inclined plane, measured perpendicular to the direction of a strike. So as we can see in the picture, this is an example of an inclined plane. So the direction there is what we call the strike, while the angle is the dip. In addition, in recording strike and dip measurements on a geologic map, a symbol is used that has a long line oriented parallel to the compass direction of the strike. That would be all. Thank you for watching and listening. God bless you and stay safe.